Welcome to another GC Basic demonstration. This is part 12 for the PIC18FxxQ24. Let's get straight into this. So this is part 12. This is graphical LCD operations using I2C. I will do another one with GLCD using SPI, but this exposes a whole lot of other capabilities. This is one of the richest demonstrations of videos that I'm doing. Okay, like and subscribe. Watch it all the way through. Okay, so number 12, using GLCD display solutions, and I've changed the title of that for obvious reasons, as you'll see. I have got all this stuff installed. I've got GC Basic, Programmer, Q24, some LEDs, some pop, switches, TTL devices, and a GLCD I2C device. Let me have a look at the desk. Oh, look, I pulled out the GLCD because, look, I've hooked up a little one. We'll have a look at that in a bit. But basically, look, I've got potentiometers, I've got switches, LEDs, a programmer, a chip, a little thing for the GLCD with pull-up resistors, which you can just make out over the back there. And we know that works because we tested that in the last video, but we will retest it because I have changed the GLCD device. Great. So I2C is a bidirectional protocol. You need to have open collector, open drains with pull-up resistors, either external as I have them, or internal to the microcontroller. Your choice. I always use externals, and we use two lines: the serial data line (SDA) and serial clock line (SCL). I might use those terms interchangeably. I apologize, but I'm going to be using 5 volts throughout my whole system. Now, touched on this before. Important things that I keep this diagram up to date. I am using for the SCL SDA port C 4 and 3 respectively, and we're going to check that circuit out. It's the first thing we're going to do. I have also got, because I am using the VDIO2, I have explained this. I need to put voltage onto here. I'm putting 5 volts into here. I am therefore using this power domain with the green pins, and within there I am using these two for I2C. I've also got a TX attached to here. It's really important that you apply the correct voltage to VDDIO for the operating voltage of the green domain called the VDDIO2 power domain. That's how I got it connected up. I have got a slightly different GLCD, but I will go back to this one for obvious reasons, as you'll see shortly. I've got pull-up resistors applied. So we spoke about this in the previous video. I'm going to send out lots of starts, lots of addresses. So I'm going to do a start, I'm going to do addresses, I'm going to send lots and lots of data around here, and then eventually sometimes I send a stop. And you'll see that it has some great impact, okay? But the first thing I'm going to do is just explain what we're going to see. We're going to see a user program, four user programs. Some of those programs are going to have user functions. Some of those are going to have converters in them. We're going to convert a BMP at one point. And these are tools that you can write on your own. They're executables that you can include within your user program. So you can actually suck in databases, BMP piles, version control, all sorts of things. And we're going to access from our user program some of the libraries, specifically the GLCD libraries. But you could go through that. So I'm saying you can go into the libraries, and then the libraries will access the low-level libraries. Things like I2C. Later on in another video, we'll do SPI. And then the compiler will generate a machine-specific hexadecimal file. In some of the demonstrations, you will see slightly different routes, because all routes are valid. The user program will talk direct to here, and then direct to here, and other things happen to generate the hex file. And so you can actually have a user program that goes direct to the low level, or and then you can code it out. There's lots of different routes that you can use, and I'll try and explain this, but this architecture of these layers exist in your mind's eye. That says, I'll just erase all the pointers, is that you have a concept of a user program at the top. You have a set of libraries, about 125 libraries that you can call upon 7 segments. We'll see a maths one today, for instance. And then there's a whole series of low-level ones. And those low-level ones, some of those are pulled in. And we can see on the compiler when it compiles how many of those are pulled in. And then each time, depending on what chip, it's a microcontroller specific solution. And that would include, obviously, the hardware as well. So there's hardware involved, and I will change the hardware as we go along. So what we're going to do is we're going to always look at the PPS, make sure the PPS is set up. We're going to make sure we've got the I2C set up in all cases. So I'm going to do that once, and then I'm going to show you 5 videos. I'm going to rerun the one that was from 170. I'm going to show you 2 that show the capability, like the primitives of using GLCD. And then we're going to do a BMP conversion. 210 will show you a sprite, and then a voltmeter. Quite a lot, but here goes. Right, I have got attached up the IDE. I've got attached up my serial port. I wonder if you can see that. Here it is. I will clear that down because we need to make sure that we can find this GLCD I've just attached. Okay, Control B to open up here, and this is the list of files I'm working on. In here I can go Control F .gcb, and it will just show me the GCB files. I'll zoom in for you and then select the filter, and it will just show me the GCB files now. I'm just moving that about. I want 170. 170. Did I actually apply that filter properly? Not sure I did. There we go. 170, show devices on serial terminal. No change to this program. I'm just going to compile that up. And we're just going to see the terminal, make sure that it actually finds my device on the GLCD bus. There we go. It's just programming it up. And it's found it on hexadecimal 78 and 79, which is what I expected. Okay. I'm going to open up demonstration 180. Control B, get rid of that. Essentially, I'll do this once and only once. So, my chip, option explicit, I have got my serial set up, and then I have put my PPS to RC3 and RC4, and those are the values that are required. I specified my baud rate, even though I don't think in this demo we'll be using it. We'll move on. In my diagram, I've updated the SDA and SCL. And then all the other constants are pretty standard. And then down here, I've got the ones to set up the I2C. And that is on port C for the data and port C.3 for the clock. And these are the 3 that you require. You need to tell it what line it's on, what's the clock line, what's the baud rate, and then you just need to say to it as a function, what is a master or it's a slave. Now, in these particular chips, you've actually got a couple of other documented controls. There's a buffer that's required. I've set it to 16 bytes, and I've muted a warning that actually tells you the buffer size. Now, after this, we're not going to look at that anymore. That's done, because the rest of this program is what we want to look at. So what we're going to do is we're going to program an SSD 1306 with 32 lines. And to do that, you include what's called the GLCD library. So that's an include statement. And that will include the file called glcd.h with the greater than or less than sign. And that will go and get that file, include it in your program, and it will then use this constant here, which that's where the gap exists. Look. GLCD type, I'm going to tell it the type, and then what that address is. The GLCD address is on 78. The rest of this puts stuff onto that little GLCD. And to be quite frank, I'm just going to program it. Let me go into Zen mode whilst it programs it. Look, I'll just pull this up. I'm just holding that for us. Has it programmed it? No, it's just doing it now. Oh, look. It says stuff. Can we zoom in on that? How do we zoom in on this? This is my control. I've had to tidy up. Still out of focus. It's focused on the back, isn't it? Well, let me reassure you that that is doing stuff. Where can I put it? How can I get that in focus? Oh, I can't get it in focus. Look. Oh, there it is. Look. You can just see it's operating. But what I'm going to do is I'm just going to pull all that out, and we're going to change this to a larger one. Look, to this one. I'm going to do that live. So I'm just going to unpower it. Oh, it was powered from the PIC1812. That's a bit naughty of me. I'm just going to do this live. There we go. I've unpowered it from the PIC1812, which I didn't realize it was pulling. I should put some volts in it. Oh yeah, as I said, I'm doing a tidy up. Now, oh, there you go. It's already powered up, the bigger one. But look, the display ratio is incorrect. Why? That's because I need to change my library. And essentially, in my source code, all I have to do is I look in the documentation. I have to change this constant. I'll pull that constant up. Get it on the same screen as you. I'm on a slightly different screen layout here. Where is it? I'm going to change this line and this line only, and it will change the library will then handle this slightly different display. Because if I look at that for you, I'll just reset the whole thing. You can see this, it's not the correct geometry. So if I open up Control B 190, the only difference in program 190 is I have taken off the -32 here. It's the only difference in terms of the setup. And now it's going to program it for us. And this time it will use the correct geometry, and you'll see that things are slightly different in here. So what I've done, I've changed the geometry, which is fantastic. Oh, there we go. Now we can see that that is correct. We've got better geometry on that. Zoom in. Can I zoom in? Now the flashing is a camera issue, not a physical issue of the code. There we go, you can see it. And in here, I'm doing the ADC read, and as I rotate my ADC, you can see that little white dot change. Oh. So I'm doing an ADC as well. So I'm reading the ADC, and you can see the value of the ADC being shown there on the GLCD at 0, and it's going up to 255. There we go. Look. It will do a 10-bit read. I've just done an 8-bit read. And you can see that it says it's running at 64 megahertz. So what we've got is a GLCD solution that's called SSD 1306. And it does things. It handles circles, lines, strings. You can integrate it with the SSD. It's not complicated. All you have to do, I'll just show you some sample code to make it work, is you use commands that start GLCD. Now, this chip we're using, the Q24, has a lot of RAM. If you didn't have a lot of RAM, then you can actually set a constant to use low memory mode. And that has a dramatic impact on performance, but it also means it doesn't use much RAM. I think it only uses 128 bits of RAM, because this is what's called a double buffered display. Everything is written to a buffer, and then that buffer is written out. And we have a set of library. The library actually supports very low mode, which is 28 bytes of a buffer, rather than the 1024 which is being used currently. And if you want to do that, you would just come into your program and change these two constants. Still work. Everything it just uses a lot less RAM and it is slower. But that's quite cool. But what you can also do is, look at this, I've put this in here. If you want to use version controlling, I'm going to use another include statement, and I can put the version number onto that GLCD. And all I have to do is, and this is running what's called a converter, and that converter will create a file for you with a version number in it. Let's have a look at that. We'll go into, change the screen mode. We'll have a look at that. And so what I'm going to do is I'm going to open up the side, the file window, move the file window down, and I'm just going to delete something for you. If I move, I just want to move things around so we can actually get it set up exactly as I want it to be. Can't do it like that. I'm going to have to move the camera. Watch this. So if I want to include a version control, which is a converter, uncomment, and then just compile up. Now compile it, and notice it says in the compilation window, build one. Let's have a look at that. Where did it say that? Build one. So every time I now do a build, it increments up something. And that file is called GCB version, and you can see it just appeared on the left-hand window. And if we open up that file, if I actually opened it up properly, it's got the number 1 in it. So something, you can't see that, it's got the number 1 in it. And what that's actually doing, quite cleverly, is actually incrementing and managing that number external to the compiler. So every time the compiler runs, it will compile that up. And how's it doing that? It's doing it because it's creating automatically on the fly for you this particular type of function. So the compiler here is more intelligent than the average compiler. It's saying here that if I wanted to find out my current build number, I would just use the variable, string variable GCB build string, and the time it was built is in this string, GCB build time str, which is string. And it will then, and you could actually put that onto your GLCD. You could use that on a terminal, LCD, etc. But these converters are pretty good. They're very robust, and you can write your own. I'll show another one. This program is program 200. I'll just shift things around so we can see it. This is the same setup in terms of the GLCD, but the include statement says include a BMP file. What? Watch this. I'm going to zoom out to the full screen. So this converter converts BMPs into GCB source. And that's it, actually dumping the file. Let's go out to the Zen mode. It's now just compiling it up. About to load GM. It loaded a BMP. Now the flashing, as I said, is not coming from it's just the cameras are here in the office. So you can see that we can import BMPs. You can write your own converter for JPEG, etc. Do what you like, I don't care. But there are a number of these converters written for you, and it is essentially using a direct call into the deep libraries. It's essentially saying here, import this file, that's what we saw in the import the file and then handle it. And essentially it creates a large table, and at the end of the day, it goes through and uses this public if statement. Here's an if statement here, look. If the current value of the incoming file is set to 0, then set it to the background color. If not, set it to the foreground color. And it's using something called pset. And pset will set a pixel. So if you write your own program, you can use line, pset, circle, whatever you like, but you can also import BMPs. In terms of memory, I think we should have a quick look to see how much memory that's used. We've got a report. Let's have a look. Assembling, that took, I don't know, 7% of the chip to put a BMP on, nothing really. I'll show you other ways of doing pictures and data later on. So the point there is that converter is converting data and it's putting it onto the GLCD through standard command set. There's nothing clever about it. 64 megahertz, that's not too bad. Control B. I want to look at another file. Using what we've seen, if I open up 210, program it. More sophisticated. Each program is more sophisticated. This is using PSET, which is the lowest level of a graphics library. It's just programming it now. That's right. It's a game. It's just bouncing a ball. It's sprite control. So you've got sprite control, and sprite control is very simple. You're actually writing direct to the buffer, and then the buffer is being put out. And the program written by Stan shows you how to do all that. But it's worth the setup at the top of this program is identical to the rest. Well, it's the implementation here that's important. Finally, this one is self-explanatory when you see it. I'll just minimize the screen. It's very self-explanatory when you see it. It's just programming it now. It's a voltmeter. So how does it do that? Well, if we look at our source program, we can sort of understand it quite easily. This is the setup for the GLCD. We've seen that before, so that's just the setup. And basically, it's overrun. Just says if it overruns the edge of the display, throw the data away. But look, I'm pulling in another library, trigonometry. So you can include a trigonometry set of calculations, trig to two places, and you pass it a parameter and a value, and it will work out and return back the results. Essentially, what this is doing, I can see it's reading the analog port, and then it's drawing that line at the specific angle for the specific voltage. And in here it says, like, read the channel, do some scaling, and scale is a function. We've seen that before. And it says here, do some maths on that. And then where's the maths in here? A bit at the bottom in a function. Here we go. Look. Sine and cosine. And then it's actually plotting out using PSET. So there's a tremendously deep set of instructions that you can use, and we can use these include statements to enrich it. And all those libraries are documented in the help. Go back to PowerPoint. So what I wanted to show you was the huge range of what we can do. In the first demonstration, let me see, I've got my pen up. You saw primitives, circles, lines, text. I spoke about the memory. You can actually reduce the memory requirement. I can change this to a very small chip and it will still work. You've seen some converters, the BMP converter. You can write your own sprites and you can actually expose the buffer, use the buffer, and then write your own routines. We should go back to 210 to look at that to make sure I've covered it properly. In this program here, this is the tables. We've seen, oh, here it is, look. This is how he's actually updating the SSD. It's called cursor position SSD 1306 fast. And look, these are the actual commands. We've seen these in my presentation. It says start, send, stop, start, send. So he's sending out the structure. He's sending out an address, he's sending out 2 bytes, and then a page number. So he's actually pushing the data out at extremely high speed. And you'd have to go through and understand how he's doing all this in here. But essentially, it's just doing an XOR and XOR all the time. We've seen use of trigonometry and some of the libraries and some low-level GLCD commands inside of Voltmeter. Extremely capable. That's what I wanted to show you. Next, we'll be doing just a flyby of SPI GLCD solutions. So it will be very similar. It will actually show the same stuff in terms of drawing lines, squares, circles, etc. But it's just an SPI. And what that does, it just shows you how to set up SPI, because the actual library could be the same library if it supports GLCD. So, but we're looking at SPI. And after that, no more graphic stuff. We'll just go lower and lower and lower. Enjoy.